Okay, for today's lab, we're going to be studying transit light curves. This is how bright a star is over time. So you notice here it's a very consistent brightness over time, except every once in a while you have these dips coming down in brightness. What does that represent? An exoplanet. How far down the dip goes gives us an idea of the size of the planet. We can use that to calculate the size. So one of the main things you need to do on the lab today is to measure how far down the dip goes. So let's do the first one together. So you look down here on the side, that's 0.5, that's 1. So it looks to me like it goes to about 0.8. Okay? Now on your lab sheet, you're going to take that under this section here called planet size. Last year they decided to go with 0.81. They thought was more accurate. That's fine. So you write that down here. Don't worry about the negative. Make it positive. You take a square root of it. So if it was 0.81, the square root would be 0.9. And then you just multiply by 10. So in other words, you move the decimal over 1. So you make it a 9. Now that gives you the size of the planet. Saturn, for example, is 9.5. So that's going to be kind of a Saturn-sized planet. So I want you to go ahead and do that for all the rest here, A, B, C, D, and E. That's for the size. The other thing we're going to do with these transit light curves, and there are questions on the test from this, is measure the distance between the dips. Okay, that represents how long it takes that planet to orbit its star. So look, it comes down here at 0.1 years. Then it comes down at 0.3, 0.5, 0.7. Well, that's an easy one then. It's 0.2. Every 0.2 years, it orbits its star. So what do we do with that? Well, here you go. Down here, this part of the lab, you're going to write the 0.2 here under period, right? Under period. Square it. That gets you 0.04. And then you're supposed to do a cube root. Now, a cube root's kind of tricky. So what I did, and what I'll do on the test, is include a cube root table. So you take this second column, the number here, 0.04, you find it here, and the number next to it on the table is the answer. So 0.04 from here, there it is, the number next to it, 0.342. That's how you do this calculationally, okay, with the calculator. We're going to do it one other way, though. There's another way to do it. So up here in this part of the lab, it says orbit distance again. That's the same thing, except we're going to try a different method here. We're going to read it right from a graph, this graph right here. Okay, this is Kepler's third law. Now here's how it works. Here's how it works. You come up here, whatever number I give you. Let's say it was a 10. You come up to 10, you come across, you come across, you come across until you hit the slant. And then I want you to pretend you hit a trap door and you fall straight down. That's it. So whatever number I get to here, let me actually do this one. 10, looks like it's just about to the 5 there. So I could guess 4.9, 4.8, or I could put a 5. Again, this one is not quite as accurate. So last year when the kids did it with the graph, they put 0.37. Okay, let's see how that compares to what we did on the calculator. In the calculator we had 0.34. That's fine. It's going to be a little bit different. You're just kind of glancing at the graph and trying to figure it out that way. Got it? And then keep in mind, what does this mean? It means it's 0.37 AUs from its star. That's really close. That's about the distance of Mercury. Okay, that's how it works. Good luck.